Okay, hello everyone. Welcome to the weekly sessions of the remote lecture series. This week we have here as a guest Professor Andrey Khalimon, Department of Chemistry and from the School of Sciences and Humanities. Today he is going to talk about the laboratory of organometallic chemistry and catalysts. Good afternoon, Professor.
Hello, yeah, good evening, I would say.
So, yeah, thanks all for joining. Once again, all the sessions will be recorded, and if you have some troubles during the lecture, you can rewatch the session on our YouTube channel. So, yeah, basically that's all. Professor, you can start.
All right, well, hello everyone. I guess it's my turn today to present my research lab, which is the Laboratory of Organometallic Chemistry and Catalysis. And it's the lab at the Department of Chemistry of the School of Sciences and Humanities. So before talking about the lab, so I'll give you an overview of the laboratory, of equipment, what we have, research, what we are doing. I would like to say a few words about myself, I guess, just to give you some understanding where I'm coming from, what is the background, and what is my area of specialization in chemistry. So initially, I received training at Moscow State University, the Department of Chemistry, and graduated in 2004 with a diploma degree in chemistry. Then I continued my education in Canada, so obtained PhD in 2010 at Brock University. And then I had two postdoctoral appointments. Both of them were kind of, in between academia and industry. So first one with the Professor Warren Pierce at the University of Calgary in Canada, and it was a project with Intel Corporation. And the second one was more even industrial, and it was in Germany, in Catalysis Research Laboratory, which is the part of one of the largest chemical companies in the world, BASF, located in Ludwigshafen, and the laboratory was located in Heidelberg, which is like 15 minutes by car from Ludwigshafen. So then in 2015, I joined the Nazarbayev University Department of Chemistry, and I'm working here ever since, and developing research program in organometallic chemistry, in coordination chemistry, mainly transition metal coordination chemistry, in application to catalysis, particularly homogeneous catalysis at most. We have some projects in heterogeneous catalysis as well, but our main focus is homogeneous catalysis. And I also serve as a part of a team of the Environment and Resource Efficiency Cluster at the Nazarbayev University. And we have some joint projects with the School of Engineering, with the School of Mining and Geosciences. So, and again, we have a space in C4 for that reason, I guess, as well. So I'm involved in a variety of different courses here at Nazarbayev University. So quite a bit of teaching obligations. So starting from general chemistry, finishing with more advanced courses for bachelor students, such as advanced inorganic chemistry, applied homogeneous catalysis, and also a couple of graduate courses, such as inorganic structures and reaction mechanism and selected topics in chemistry. So with this being said, I would like to talk about the lab. And our lab is called Laboratory of Organometallic and Catalysis, and we are dealing mainly with transition metal organometallic compounds and also coordination compounds in application to catalytic reactions of mainly organic transformations. So we have three laboratories, three rooms. One, and I would say this is the headquarters of our lab, and it's located in block 7, room 508 on the 5th floor. The second lab that we have located in block 9, it's 310 on the 3rd floor, and we also have a small space in C4. Well, it's small, but it's still very functional. about members and the website. So chemistry department has created quite a nice website, new website with all the faculty profiles and research groups profiles. And you can also visit my personal research group website for more information. So these are the pics from the lab, photos from the lab. I will mainly show you the 508 laboratory in block 7. Simply because of this situation with pandemic, we don't really have access everywhere, and we had to divide our team in several groups. One group has only access to block 9, another one has only access to block 7, and the third one has an access to C4 building. So this is 7508 laboratory. It's reasonably small, in fact, but that's what we started with initially. And I would say we turned it to a very functional workspace. So despite the fact that this is small and has only one fume hood, we still managed to do quite a bit of chemistry in there. So most our chemistry is about dealing with air-sensitive, moisture-sensitive compounds. So we have to work under inert atmosphere. Typically, we use argon, high purity argon. Therefore, we do not necessarily always need a fume hood in order to do this chemistry because everything is in a closed system, so it doesn't smell. But of course, if you're dealing with some smelly stuff, and we do have some toxic compounds that we unfortunately have to deal with, you cannot really avoid it in chemistry. So you have to use the fume hood. So we are using so-called Schlunk lines. So this is the vacuum argon manifold, which has two lines. One is a vacuum line, another one is argon line. And I'll show you some of these lines a little bit later as well. So we have to, first of all, remove the air from our vessels, then fill these vessels with argon, and then do the chemistry in argon. And we also have inert atmospheric glove boxes. We have two of them. One of them is located in block 7 lab. Another one is located in block 9 lab. So that we don't have to run between different blocks, in order to perform some manipulations in these glove boxes. But these are really nice. So the glove box in block 7 is hooked up to the solvent purification system. So we have to dry our solvents and remove oxygen because otherwise compounds will decompose. So you can do it manually, but it takes a lot of time. So we have an automatic system that does it for us. We can simply just collect pure solvents from that system. So, and it's also hooked up to electrochemical station, so we can perform some electrochemistry inside the glove box, electrocatalytic reactions, for example, and many others. Okay, so this is almost all the lab on this picture. So some of these people are gone by now. Some graduated, some continued their education in graduate programs abroad. But this is picture taken in, I believe, March or something like this. So this is quite recent, right before the whole pandemic situation. And we are interested in development of novel, economical, and efficient catalysts or catalytic systems for different organic transformations to prepare a variety of value-added organic chemicals, to simplify already existing technologies for preparation of these specialty organic chemicals, for example, pharmaceuticals, agrochemicals, and many others. But we're also interested in different processes that are relevant, sort of relevant to the search of alternative energies and alternative carbon sources. For example, we would like to use carbon dioxide in chemical synthesis. So, different chemical companies are very interested in using carbon dioxide as a reagent, as a carbon source, not because they're trying to save the planet from the global warming. No, because carbon dioxide is very cheap, very abundant, and it's inert, non-toxic carbon source, right? So, and on top of that, a lot of countries have different regulations about CO2 emissions, and the companies have sort of quotes for CO2 emissions, right? So if they can use the CO2 from one of the processes in other processes, they can emit more CO2 from third one, right? So therefore they can get more profit. So frankly speaking, for chemical companies, it's all about money, it's all about profit, but of course they're trying to care about the environment as well. And that's the reason why a lot of chemistry, industrial chemistry, is already involved catalysis, but it's already switching. It's also switching in new process to catalytic reactions as well. So our research is touching many aspects of synthetic chemistry, including synthetic inorganic chemistry, synthetic organic chemistry, different fundamental aspects of coordination chemistry, structural and theoretical aspects of organometallic compounds, including bond theory, ligand design, mechanisms of the reaction. So it's a combination of different fields of chemistry, in fact, and you cannot really call it pure organic or pure inorganic. It actually involves everything: organic, inorganic, physical chemistry, because we study the mechanisms, we study the kinetics and thermodynamics of these reactions. If you know the mechanism, we can improve our systems and make them more selective, more active, and more appealing in general. So, and we utilize a variety of different characterization techniques, but majority of our work includes NMR analysis. So we monitor our reactions spectroscopically. And also we would like to establish the structures of our intermediates, catalysts, and other species involved in the reactions. So we use the single crystal X-ray diffraction analysis. So unfortunately, we don't have a single crystal X-ray in Kazakhstan, so we have to collaborate, and sometimes it's painful because you have to send the samples abroad, and it's not that easy to do here. So there are a lot of restrictions and regulations regarding this, but nonetheless, we still manage to do that, and I really hope that in the nearest future, the chemistry department will get the single crystal diffractometer as well. So, and this is a nice citation from Alvin Mitash, and he was an industrial chemist in Germany, involved in catalysis and organometallic chemistry. And I would like to show this citation because this is actually true. And if you look at the modern chemical industry, you'll realize that it does not exist without catalysis. So you have to use catalysis in transformations. And he was saying that the chemistry without catalysis would be a sword without a handle, a light without a brilliance, and a bell without a sound. And that this is absolutely true words. All right, so we are interested in catalysis. And in order to develop these catalysts, we are doing organometallic chemistry. So in terms of equipment, we pretty much have everything what we need, except the single crystal diffractometer. But we have a standard synthetic chemistry equipment, including different magnetic stirrers, glassware. We have a special glassware, in fact, because our compounds are air sensitive. So we have to use Schlunk techniques, Schlunk glassware, and I will show you how these flasks look like in a little bit. But we have drying ovens, fridges, freezers, rotavap, sonicators, all of that. I mean, this is very standard, and pretty much any synthetic chemistry laboratory has these types of things. And we do have them as well, so there are no problems here. So these are the lines that we are using. They're called Schlunk lines. So essentially, the line consists of two tubes that are connected to each other through these valves. There are two ways valves, so you can turn them either on argon or on vacuum. So, and you can connect this line. This line is connected, first, the vacuum line is connected to the vacuum pump, and the argon line is connected to the tank of argon. So we can monitor our vacuum level. So we have these manometers here. And with this particular line, we can achieve 5×10⁻⁴ bar. So this is quite amazing vacuum, in fact. And we connect this line to the so-called Schlunk Flask. So this is the flask, like a regular round bottom flask, but it has the side arm, which has the valve, because you can close it, right? So so if you close it and fill it with argon, everything would be under argon. So the same, you can evacuate it on vacuum and things like that. And the solvents are also stored in special flasks as well. So everything is stored under argon. And we do large-scale reactions using these lines. So one of them is a commercial line, so it's from Sigma Aldrich, and another one is actually custom-made line. So there is a glass blower in Canada who happened to be my friend, and he just made it for me. And I brought it personally by myself from Canada to Kazakhstan. So this is very unique line. You will never find anything like this anywhere. And it's really cool, actually. It's amazing line. It's a lot better than commercial available lines and a lot cheaper as well, in fact. And we do large-scale reactions using these lines, but for the small-scale reactions and for the storing of our compounds, we use the glove boxes, inert atmosphere glove boxes. So here is one of them, which is staying in the Block 7 lab. So this glove box, it's a single station glove box. We have two of them, as I mentioned before. Both of them have freezers. So you can store your compounds in a freezer under inert atmosphere. So inside you have, of course, the balance, you have stirrers, you have a variety of different things. So, this glove box is also connected to the solvent purification system. So you can actually open it up in a glove box and you'll have the solvent running, dry and oxygen-free solvent, so absolutely pure. And of course, we can monitor the levels of moisture and oxygen in our glove boxes. So there's a screen with an oxygen sensor connected to it and the moisture sensor connected. So we can see what is the level of oxygen and moisture. So, and there are two antechambers, two ports, one small one, one large one. So the large one is used only in occasionally when you have to pump in something very big, essentially, right? So, but this is the routine antechamber that we are using. And the glove box, it's, I don't know if you know the principle of operation of the glove box. So essentially, there is an air, well, not air. There is an argon inside, but there is a wind of argon inside. So the argon is circulating in the glove box constantly by the pump, and it's constantly being purified through the two columns of the catalyst, and the catalyst is not working forever, so you have to regenerate it. But typically, this is not a problem at all. And we are doing these regenerations not very often, in fact. So the quality of our gases are okay. So this is how we are working. Essentially, the main workstation, this is the line. And then if you want to prepare the samples or store compounds or set up small reactions, some NMR scale reactions, so you can use the glove box as well for these types of the transformations. So here's just an example of how we work. So essentially, everything should be done under argon atmosphere, right? So everything is air sensitive. You always manipulate with the pressure. So all simple things like filtration, solvent evaporations. So everything is done on the line. Nothing is done outside the line. So here's, for example, you can see the filtration process. So we have this stainless steel cannulas with the filter on one side. We use the rubber septum, and so we increase the pressure in the first flask, and then we decrease the pressure in the second flask. We just insert the needle. And essentially, using the high pressure here, the solvent is driven to the second flask. And because we have a filter here, so the solution is being filtered. So it sounds a little bit tough when you do not do it yourself, I guess. And when people come to the lab and work for a couple of first days, they some of them nearly crying, saying why it's so difficult, why it is supposed to be so difficult. But then you get used to it, and essentially you just it's a routine process for you, and nothing is really complicated here. The only difference with a simple organic chemistry, classical organic chemistry, synthetic chemistry, is that you always have to think about air sensitivity of your compound. So before you do any manipulation, so you have to think twice, 3 times what you're doing. Otherwise, you will do some synthesis, right, which will take weeks sometimes. And then one simple mistake, you just have an exit in air somewhere, and everything is dying, everything is decomposing. So this is not very pleasant, all right? So, and of course, I mean, everybody does mistakes like that from time to time, but you know, you do it several times, 10 times even, and then you will not do it again because you don't want to waste your own time, and you don't want to waste your own effort to make the compounds, because if everything dies, you have to start from scratch. So this is very important in our chemistry, to think about air sensitivity always. So from other equipment, as I mentioned, we have some electrochemistry station hooked up to the glove box. The whole setup is outside the glove box, of course, but the electrodes are inside, so you can do the chemistry inside. So we are getting right now several bar pressure vessels. So this is stainless steel reactors for catalytic reactions with gases under the pressure. So because we are entering a huge project with the CO2 chemistry in collaboration with the School of Mining and Geosciences, so we need to do some high pressure transformations as well. So these things, they hold up to 200 bars pressure at 300 degrees Celsius. So it's amazing how tough they are. And we are using NMR spectrometer. So we have 500 megahertz NMR spectrometer located in the shared facilities, but not that many people, fortunately, not that many people are using NMR at Nazarbayev University, and we have quite a bit of time for this. We also have, for very routine analysis and pretty much for some maybe ligands and or organic transformations, catalytic transformations, we have benchtop SpinSolve 60 megahertz NMR spectrometer. It's located in block 9. So it's actually quite small. We can run NMRs on simple compounds using this very simple spectrometer. So it's not utilizing any liquid helium or liquid nitrogen, so it's a very handy, in fact. Okay. Just want to say a little bit about the group members. Our group started in 2015, and at that time it was very tiny. So I had 2 students only, and it took us a while to get a research space, laboratory space. But when all this happened, so we started growing. Right now, 3, 4, 5, 7, 8 people in the group, but there were times where we had 10 people in the group. So we have three PhDs working with us. Dr. David Arapetyan, so he's an independent postdoctoral fellow hired by the Office of the Provost, but he's collaborating with us, helping with some organic transformations. Dr. Zgura Stopku, he's the instructor in chemistry, and he is actively involved in research as well. Despite the fact that he doesn't have to, so he has mainly teaching obligations, but he's very curious about organometallic chemistry, and he's coming from a very nice research group in Austria from the Technical University of Vienna, from the Karl Kirchner group, and his PhD is about organometallic chemistry, in fact. So he's very happy to contribute to research in our group as well. One postdoctoral research assistant, so Christina Godun, she's with us for a really long time already. And I don't know how to live without her anymore, because apart from the research, she is also involved in a variety of different administrative activities, including procurement and many other things. So she's helping a lot with that, and I'm really thankful to her for this. So, but then we have, currently we have one master's student, Aziza Dilkhanova. So she's finishing her master's thesis this semester. And we have some bachelor students as well. So Rahan Zakarina, so she's finishing her BSc program this semester. Valeria Frolova, who's the third year chemistry major student. And also Azamat Isingazin, who is the second year chemistry major student. And on a volunteering basis, Ainur Slamova, who is the research technologist from core facilities, she's also doing research in our lab, helping many others with NMR analysis, some kinetic studies, but she's also involved in separate projects in catalysis as well. So we already have quite a few alumni in our research lab, and majority of the people who graduated and left Nazarbayev University, they are continuing their graduate studies abroad. Alibek Nursid, so he just a year ago defended his master's thesis in the School of Engineering and Chemical Engineering. So right now he's working in, I don't remember exactly the name of the company, but this is like a subsidiary company of Kazmunaygas. So, and he actually called me recently and told me that it's an interesting thing. So they hired him as an engineer, chemical engineer, but they asked a lot of fundamental chemistry questions. So as difficult questions, and he was quite well prepared for that. That's a good thing, I guess. A lot of people are in Canada, in my former university, continuing PhD and master's degrees in organometallic chemistry and catalysis. Some people moved to states, Purdue University, Florida State University, and some people still at Nazarbayev University in different schools, School of Medicine, School of Engineering and Digital Sciences, and so on and so on. But most of the people are actually, either employed or continuing their education. So this is very cool to see, because it's always cool when you see people from your research lab are doing well. So this is very great. So we are collaborating with quite a bit of different institutions and universities in Kazakhstan and also abroad. Of course, at Nazarbayev University, we collaborate with other groups at the Department of Chemistry of the School of Sciences and Humanities. But we also have collaboration projects with the School of Engineering and Digital Sciences, with Chemical Engineering Department, and also with the School of Mining and Geosciences. And actually with the School of Mining and Geosciences, we just received the Collaborative Research Program grant, which is very large. So it's $150,000 US per year. and we are dealing with the CO2 storage and CO2 conversions as well. So it's a big combination of chemistry and geoscience, and it's a very interesting interdisciplinary project. So we also collaborate with the Kokshetau State University, in particular with Laboratory of NMR Engineering Profile, and Karlsruhe Institute of Technology, and particularly with the Institute of Catalysis Research and Technology in Karlsruhe. We have collaborators from Lomonosov Moscow State University in Russia, from the different research institutes of the Russian Academy of Sciences, and also we collaborate extensively with Brock University, Chemistry Department, Brock University in Canada. So quite a wide collaboration network. But well, I forgot to mention as well that we also have collaborators from the Technical Institute of Vienna. So at least with the crystallography. So a lot of different people from different kind of disciplines involved in collaboration. So we have engineers, we have geologists, geochemists, we have computational chemists, we have synthetic organic chemists, synthetic inorganic chemists as collaborators. So this is quite cool because in fact, when you think about catalysis, it's a combination of all of that. So it helps a lot to develop very interesting catalytic systems. So now I would like to talk a little bit about chemistry and about research, what we are doing in our labs. So I already mentioned that we mostly focus on molecular inorganic chemistry, coordination chemistry, organometallic chemistry. And particularly, we are trying to develop different economical, abundant, and efficient and selective catalysts for preparation of commodity and fine chemicals. So nowadays, if you look at the industrial interest, I would say in the interests of chemical industry, of course, they're interested in development of new products, but we already have a plethora of known products that are essential for our life. But very often these products are produced through technologies that are developed or were developed really a while ago, and they are not very economical, I would say, in terms of the energy, in terms of the manpower, in terms of many other things as well. So they're not very environmentally friendly. And so one of the purposes of chemical industry nowadays is to switch from these, old and expensive technologies to modern, cheap, and at the same time green technologies. So green, it means that, less wastes are produced, but in terms of the, profit of the company, they spend a lot of money on utilization of this waste. So of course they don't want to produce a lot of waste, because otherwise they will spend all their money on the waste treatment. So our research interests generally include homogeneous catalysis for sustainable chemical and energy technologies. So we'd like to contribute to sustainable chemical production. We are interested in activation of small molecules by transition metal complexes for their conversion into liquid fuels and chemical feedstock. Molecules like, for example, carbon dioxide, ammonia, and others also, carbon monoxide, things like hydrogen, and so on, nitrogen. So we are interested in development of abundant catalysts for selective transformations of organic compounds, and this includes chemoselectivity, regioselectivity, and enantioselectivity. If you think about catalytic process that is being applied in industry, so the main requirement for this catalyst that it should be selective. Selectivity is the priority for chemical industry, and it's a lot more important than the catalyst activity, in fact, because now industry is switching to flow type chemistry, in continuous type chemistry, and activity doesn't really play that important role anymore, but the selectivity does, because if you make several products, it takes you really an effort to separate them, and it becomes quite expensive. And we're also looking at the organometallic approaches to solar energy harnessing. So we're trying to develop different systems that can be involved as dyes, for example, in dye-sensitized solar cells, or that can act as a photocatalysts, right? And I mentioned before that a lot of our research is involving different physicochemical characterization techniques, spectroscopic techniques. We study the reactivity properties, study the mechanisms of catalytic reactions. So it's a lot of physical chemistry, kinetics, thermodynamics. So all of that is very important. So this is necessary in order to develop even better systems with more controlled properties and more controlled reactivity patterns. So, and this affects the selectivity, activity, stability, and other things. The whole idea of catalysis comes from an idea of green chemistry, and green chemistry is extremely important nowadays in chemical industry, in chemical production. And there are essentially 12 principles of green chemistry. They're shown here. They do make sense, and in fact, if you follow all these 12 principles of green chemistry, you start doing chemistry in more economical way. So you start saving a lot of money. So first of all, of course, you have to prevent wastes. You have to think about atom economy. Atom economy means that all atoms that you have in starting materials have to be converted to the products. So none of them is lost. So you have to use less hazardous systems, compounds, synthesis, design benign chemicals, use renewable feedstock, reduce derivatizations, and so on and so on. And if you look at the principle number 9, it says catalysis. So you prefer to do catalysis versus stoichiometric reactions, because catalytic reactions are typically more atom economical reactions, and therefore they produce less wastes and allow for transformations to be achieved in a more selective fashion. Catalysis today is a key technology for development of chemical industry in general. And if you look at the plethora of all the chemicals that we are produced in petroleum industry, in pharmaceutical industry, and so on, that more than 90% of all these chemicals are produced using catalytic reactions. And on top of that, catalysis allows to do transformations in a more greener way, minimizing wastes. So if you think about organic synthesis, where are all these wastes coming from? Well, typical classical organic transformations that are most wasteful are oxidation reactions using stoichiometric oxidants and reduction reactions using stoichiometric reductants. Right, so they produce enormous amounts of waste, and particularly inorganic waste. And inorganic wastes are very hard to deal with, very hard to treat, very hard to utilize, and it's pain in the neck for any chemical company, in fact. So we would like to do these reduction transformations, because reductions are fundamental in any organic synthesis, essentially. But we would like to do it in a catalytic way. So we're looking at 3 types of the transformations. So this is hydrogenation, hydrosilylation, so it's addition of hydrosilane across unsaturated bonds, and hydroboration reaction, so it's addition of hydroboranes across unsaturated bonds. Historically, majority of these transformations are, well, they are known. They're known for quite a while, in fact. But the majority of these transformations historically are done using quite expensive, these heavy late transition metals: ruthenium, rhodium, palladium, iridium, platinum. So all these metals are expensive because their natural abundance is extremely low. So if you look at this plot of the natural abundance, relative natural abundance, you see that the metals that are mostly industrially used for these types of the reduction reactions are located at the bottom of this plot. So we would like to do the same chemistry, absolutely the same known reactions, but using completely different catalysts based on more abundant elements that are located on the top of the plot. Particularly those elements, those transition metals that are produced in industry on extremely large scale, such as iron, nickel, zinc, cobalt, copper, and other things. So therefore, we would like to switch from these metals, which are very expensive. Rhodium is extremely expensive actually nowadays, to these metals, which are very cheap because they're very abundant. So of course, if we can switch from rhodium to iron, we can save a lot of money for any chemical industry. And this is the whole idea, but it's not that easy to do, in fact, because the properties of the first row transition metals are very different from the properties of the second and the third row transition metals. So they're very often involved in one electron transformations, where classical catalytic reactions typically occur with two electron reactions, two electron transformations. So therefore, you have to, to do a very careful design of your catalytic system based on the certain ligands and certain oxidation states of the metals, and so on and so on. So I will not go into details of this design because that requires particular, I would say, knowledge of transition metal chemistry. And I guess, unfortunately, at the chemistry department, we teach this only in a fourth year. Well, we used to teach this in the fourth year. Now we actually switched to the third year because we thought it's already too late to teach this kind of things. So, but the general idea is that our catalyst design should be based on two things. First of all, we are looking at the cheap metal, right? So it's supposed to be abundant. It's supposed to be not very toxic, for example, iron or nickel. Well, toxicity is a very interesting thing. Everything is frankly speaking, is toxic, right? It depends on the little dose. Even sodium chloride can be toxic if you take kilos of it. But usually heavy late transition metals, they are more toxic than the first row transition metals. So rhodium would be more toxic than iron, right? So and platinum would be more toxic than iron. So we're looking at the abundant cheap metals that form stable complexes, and for that we need to design certain ligands, and they're supposed to resemble the properties of the precious metals. Again, this is about ligand design. But when we think about the ligand, a lot of people, when they design complexes like this, they start using very sophisticated ligands, and they forget that the ligand also adds the price to the cost of the overall catalyst. And sometimes ligand is more expensive than the metal, right? So we are looking at very simple ligands, either commercially available or ligands that can be derived from very easily from commercially available sources and cheap sources as well. But we also need to think about the ligands in terms of the tuning of our system. So we have to have different possibilities, synthetic possibilities to tune the sterics, electronic properties of the ligand, and the whole synthetic procedures, the whole synthetic chemistry should be easy to handle. So, and one of our approaches is to utilize so-called pincer complexes, because the ligand here holds the metal like a pincer. So it just sort of takes the metal. Typically pincers have symmetrical structure. We have the same donors in sidearm positions, and there can be different donor in the bridgehead position, but we're interested in non-symmetrical pincers. For example, like this. This allows us to tune the sterics and electronics of the sidearm groups here a little bit better, and therefore we can control the properties of the catalyst. But we also use simple commercially available salts as a pre-catalyst, and this is another very interesting approach, salts that people never thought to be used in these types of the reactions. So they're extremely cheap, they're air stable, so, and we can use them as a pre-catalyst as well. And I will show you a few projects. So the first project is dealing with the development of base metal catalysts for reduction of challenging unsaturated molecules. Challenging those where the unsaturated bonds is deactivated essentially for addition reaction. So if we look at the different molecules that have unsaturation in organic chemistry, of course, we have alkenes, alkynes, and so on and so on, but we are interested in carbon heteroatom bonds because we can produce very reactive products that can serve as starting materials for further derivatization and further organic synthetic chemistry. So, for example, if you, well, this is not deactivated, these are ketones or aldehydes, so they're easily reduced to the alcohols. But the ester or amide is already deactivated because the carbonyl carbon has less electrophilic character in comparison with ketonal aldehyde. So, and this produces interesting things. So reduction of esters, for example, is relevant to production of biofuel, because anything what is bio essentially has an ester group. And you can convert these ester groups to alcohols, and alcohols can be used as fuel. Reduction of amides, carboxamides allows to produce variety of different amines. And for any chemist, it's not a secret that amines are used as versatile syntones and starting materials for a variety of different biologically active molecules, natural products, pharmaceuticals, agrochemicals. So utilization of amines is really broad. And if you can use a very simple method to prepare a variety of different derivatives of amines, this is very cool. And also nitriles, for example, so installation of nitrile group or cyana group in organic chemistry is very simple. It's one-step catalytic reaction, in fact, as well. It's hydrocyanation of alkenes, for example. So, and then if you can prepare imines or amines from nitriles and use them in further synthesis of more complex nitrogen containing organic molecules, this is also very useful transformation for specialty chemical industry, such as pharmacy or agrochemistry. And of course, pyridines, the same idea. So we have nitrogen containing organic molecules that can be used further in the synthesis. And other molecules that are not shown here, those are nitro compounds. So nitro compounds, aromatic nitro compounds, are extremely cheap. So this is essentially the starting point in chemical industry, how you get any nitrogen containing organic molecule. And then if you can convert it in one pot manner to a variety of different molecules, products, this is very, very cool for specialty chemical industry. So, I mean, probably one of the most important element, heteroatom, that is used in organic synthesis for pharmacy, for agrochemistry, functional materials, biological active molecules is nitrogen. Right. So, and if you can interconvert different nitrogen containing organic molecules quite easily using catalytic reactions, this has a huge impact on the production technologies. So apart from them, as I mentioned, so we are interested in nitrogen, right? So apart from this, nitrogen silicon and nitrogen boron containing products are useful synthetic intermediates. For example, they're used as silylating agents, as coupling reagents, iminium ion generators, and monoboryl amines have been shown recently to be very cool reagents for production of aldamines. So that was a quite recent publication in Angewandte, actually. So first project that was sort of, well, that initiated the whole thing in this chemistry was the reduction of amides. And we are still doing that, but using different approaches. So reduction of amides is, frankly speaking, quite challenging. Because first of all, nitrogen is an electron donor, so it's sort of killing electrophilic character of this carbon here, and therefore it's deactivating the carbonyl bond for reduction. So there are different approaches that result in either CO bond cleavage or CN bond cleavage. Typically, hydrocellulation and hydroboration can be used. Hydrogenation is used to a lesser extent. But reactions are not very selective. So there are a variety of side products that include the C-end bond cleavage, and we form alcohols, aldehydes, and mixtures, and everything has to be separated. So it's a nightmare essentially. Apart from that, we have to have some external activation. It's either thermal activation, so the temperatures are rather high, more than 100 degrees Celsius. So for homogeneous catalysis, this is high temperature because homogeneously catalyzed reactions are mostly exothermic as well. And it's very difficult to control this heat when you do it on a large scale, or photochemical activation, which is not very, a good thing, I guess, if you start thinking about application on a large scale. Reactions usually take a long time, up to 74 hours. So none of the industrial processes actually take that long. So 72 hours means that 72 hours the company doesn't get the profit. So they don't want to run reactions for 72 hours. So the maximum they would like to run reactions for 12 hours, which is overnight. Set it up at night, come in the morning, get the product. So, and I already mentioned the selectivity issues. On top of that, mostly precious metals were used in these transformations, and we were able to show the significantly improved conditions for very simple cobalt salts, such as cobalt dichloride. Cobalt dichloride can actually act as a pre-catalyst for these types of the reactions, or cobalt acetylacetonate or cobalt acetate, with very simple ligands such as triphenylphosphine. And reactions occur mostly at room temperature. Some occur, problematic ones occur at 65 degrees Celsius. So this is a lot simpler than all other systems that published before, using very expensive metals and very sophisticated ligands. So we were lucky that we found this type of the reactivity, but we were aiming for this reactivity. It's not like we just, we're pointing at the sky with the finger and trying to hit something. No. We were aiming for this particular reactivity, and I guess chemistry is very often about luck, but as one Nobel laureate said, you become a lot more lucky if you work 24/7. So that's true. So that was one of the projects. It was published in 2019 in ChemCat Chem paper, and actually this paper so far has been very popular, and it even received the Web of Science award as the paper with the high citations, paper in chemistry with high citations. So for this paper, I got an award in 2019. Science Leader, Web of Science. Another project, so that was an example of commercially available salts that can be used as a pre-catalyst, but we also do a particular design of our catalyst with the certain ligands, and I was talking about pincer ligands. So we make the series of nickel complexes. Some of them are shown here, so they have been structurally characterized. So these are single crystal X-ray structures of these molecules. And we showed chemoselective hydroboration of aldehydes in the presence of a variety of different things, even in the presence of ketones. So imagine that you have a molecule that has a ketone and an aldehyde group. So you can reduce selectively aldehyde and your ketone will remain untouched. So, but it also was the first system for hydroboration of amides, including more challenging secondary and primary amides as well. So usually tertiary amides are reduced a lot easier than secondary and the primary ones. So that was another publication in Dalton Transactions in 2019. And this is rather long paper, really long project, in fact. And it has a lot of mechanistic studies, including computational mechanisms, which was performed by my colleague from the Karlsruhe Institute of Technology. So this Philip Plesso, he's amazing computational person. So absolutely amazing. I've never seen anybody like this before. So he first of all knows organometallic chemistry, but then he's a very good theoretician as well. So a little bit of modifying our ligand, we made another nickel complex with the secondary amine sidearm here, an H bond, and this complex was used as a catalyst for transfer hydrogenation of carbonyl compounds. So transfer hydrogenation, it's when you do the hydrogenation as it would be done with the molecular hydrogen, but you don't use hydrogen. So you use something that gives you hydrogen during the process. And particularly we use isopropanol, which was as a solvent and the hydrogen source. So we first dehydrogenate isopropanol, form acetone as a byproduct, which can be easily separated from the reaction mixture. And then we can reduce any ketones and aldehydes. And this was the first system with nickel that does a reasonably good job in transfer hydrogenation reactions. So before, nickel systems had really low activity or required really long reaction times or high temperatures. So these reactions are comparable with the state-of-the-art ruthenium complexes, which, by the way, deserved the Nobel Prize a while ago. So that was published quite recently in Dalton Transactions as well. I forgot to note, actually, guys, so that all of these publications here that you see, they involve actually a lot of undergrad students. So, for example, Sigizbayev Midyat, Dimash, Din Muhammad Shahman, so these are two undergraduate students. If you go back in the presentation here, so the Midyat Sigizbayev, Asel Adamov, who else? I guess that's it. So these are also undergraduate students. Publication before, it's Alibek Nursid, Jaisan, Aisha Kasembek, Midyat again, Sigizbayev. So these are also undergraduate students. So we are doing a lot of research with undergraduate students, and undergraduate students can do a lot of research. So please do not believe people who say that undergrads are useless in the lab. No, they're very useful. Later we started looking at other transformations, and particularly we would like to make different nitrogen organic molecules, and we started looking at the hydroboration, double hydroboration of organic nitriles. And this part of the projects, we continue still doing this. This is about interconversion of nitrogen-containing functional groups. It's relevant to the specialty chemical synthesis. And so for double hydroboration, these are examples of already published base metal complexes. So they either require reasonably harsh conditions, such as high temperatures, they show low conversions, or the use of quite sophisticated ligands, like these radicals here, these radicals here, these radicals. So this adds a lot of price to the whole system, despite the fact that we use cheap cobalt. And in this case, we used cobalt acetylacetonate with commercially valuable DPE-FOS ligand shown here. So they're both reasonably priced for most active, I would say, hydroboration of organic nitriles at room temperature. And apart from that, we realized that we selectively get these bis-baryl amine species, and we thought that B-N bond can be labile, and we can in situ utilize these compounds in the further synthesis, organic synthesis, and we report very efficient and selective transformation of these boryl amines to aldimines. So essentially, we can do this transformation from nitriles to aldimines in one pot. We do not isolate these things here. And this is amazing because nitriles are very readily available. They're very cheap. And then we can get a variety of different aldimines. They're very useful for specialty chemicals. And the yields up to 99%. So guys, this is yields for 2 steps. So essentially, the hydroboration is quantitative. And then we have some loss a little bit here in the second step. But the reaction works very well. We showed applicability of these transformations for different aldehydes. So, and we can use only aldehydes, not ketones. So for ketones, the reaction does not work. So, and we also showed a very good functional group scope for the different nitriles. So the reactions are quite selective, so they tolerate many different functionalities, including those that typically prone to reduction, such as esters here, the amides, lactones, and inactivated double bonds as well, so carbon-carbon double bonds. And this is very cool. This research was recently published in Chemistry European Journal, and it has been quite popular. And probably a month after this publication, so this paper was highlighted by Synform journal, and the Synform is the German journal that is complementary to Synlet and other journals, and it shows trends, views, and state-of-the-art transformations in organic chemistry. So, and the paper was highlighted as a Syn story. And Syn stories typically feature new advances in synthetic organic chemistry, which are accompanied by the author's views. So I had an interview for this paper in Synform, and that was quite nice that that our research at Nazarbayev University was highlighted by one of the leading synthetic chemistry journals and publishers in Germany. So that is really cool. So the other projects that we are dealing with, they include base metal materials for wastewater treatment. So essentially, this is done in collaboration with the School of Engineering and Digital Sciences, Department of Engineering and Materials, Chemical Engineering and Materials Engineering. So we use our knowledge of homogeneously catalyzed reactions to prepare different heterogeneous catalysts. And one of the master students who graduated a year ago, the Alibek Nursid, so he was actually doing masters in chemical engineering while working in my laboratory, and he developed the cobalt-based composite materials for selective and efficient reduction of nitrophenols, which belong to the list of emerging pollutants. And they're very hard to remove them from wastewaters, industrial wastewaters. So we used simple cobalt-based composite materials, heterogeneous catalysts for these transformations. So I'm not showing a lot of pictures here, and because this stuff is still unpublished, so it's and I don't really want to cause some troubles in the future for this, because we will publish this very shortly. And in other directions that we are pursuing, we design complexes with different polyaromatic ligands for photocatalytic and electrocatalytic applications, and also for potential candidates as dyes for dye-sensitized solar cells. So ligands like azulene-based ligands, which are natural chromophores, in complexes with these ligands. So we would like to do some electrocatalysis and photocatalysis. Maybe these ligands will induce some interesting metal ligand collaborative transformations through the redox active, ligand modifications. So, and we're interested in photocatalytic and electrocatalytic reduction of CO2, for example, to carbon monoxide, which is the part of the syngas and widely used in Fischer-Tropsch synthesis and petroleum industry. And we would like also to produce catalytically hydrogen from water and many other products as well. So this is essentially the overview of the projects that we are currently involved in. We have 2 grants at the moment. So I have the Faculty Development Comparative Research Grant about the reduction of challenging unsaturated molecules. And this is the 2nd year now of this grant. So I'll probably apply for another one actually at the end of this year. And I also serve as a co-PI for collaborative research program with the School of Mining and Geosciences about geothermal energy production, about carbon storage and sequestration, and utilization of CO2 as well. So, and this is huge. So it just started this year, and the grant has a budget of $150,000 annually for 3 years. So the faculty development competitive research grant has $50,000 per year for 3 years. I was also involved previously to a new RAU grant, which allowed us to, it was big as well. So it was $100,000 per year for 3 years. And it allowed us to, create our own library of reagents and consumables that we more or less become independent on procurement. So we have to fill this library of things, right? Constantly renew the feedstock, but it took us a while because procurement at Nazarbayev University takes quite a long time. And for example, you want to switch some, acyl group is the methyl group, or acyl group is the propyl group. So you have to wait for several months. And we had to do it before, but not anymore. So we have actually 2 storage rooms in Block 7, one full of chemicals and another full of other things. So, we can do our research uninterrupted without waiting. And this is a good thing because in order to be competitive, internationally competitive, right? So time is essentially money. So you have to be fast. Otherwise, somebody will do it instead of you. Especially if you work in such competitive fields as a CO2 reduction or things related to pharmaceutical industry and things like that. So more or less, we are in a really good situation right now in terms of the funding, in terms of the chemicals availability and consumables. So we do not have any breaks in our research. Even pandemic didn't stop us. So we are in the lab every day. And we're not only working, sometimes we are having fun as well with the group. And here's picture, Christina and David having some lunch in Borovoy. So we had a weekend trip. And from time to time, we just get together somewhere. And unfortunately, right now, it's not that easy to do, but hopefully by summer, if everything with the COVID will not accelerate anymore, so we can travel somewhere together as a group. Maybe Borovoy again would be an interesting trip. So if you want to have more information about the lab, about projects, about the group members, you can always visit these 2 websites here. And if you have some general inquiries, we can talk about the chemistry, or if you want to contribute and or you have some ideas and you would like to accomplish these ideas using our facilities, you can always contact me. So my contact information is here. I'm always happy to see very enthusiastic students. Sometimes people are scared. They believe that this research is very difficult because it's air sensitive and it has a lot of nuances and things like that if you are motivated, if you're interested in any project, you will learn things no problem at all. So, and we are here to train you. But first thing what you need to do is to get motivated. So your motivation is extremely important. But if you're doing it just on the side, it's not very important for you, then probably don't even start, because chemistry requires a lot of dedication and time. And it's rewarding at the end, but it does require a lot of dedication and time. So you have to spend a lot of time in the lab. All right. Well, this is it, what I wanted to show you today. If you have any questions, I can answer. I'll be happy to answer them.
So here in the chat box, we have our first question. It says from the Sultanate, good evening. Do you need data analysis in chemistry projects?
Sometimes, yeah, because when you collect a lot of data for catalytic reactions, so imagine that you have several reactions. You can utilize different conditions. You have kinetics, you have thermodynamics, so all of these numbers, right? So you have to really do something with this, right? And in fact, if you're thinking about transferring your system from academic laboratory to industrial applications, so you have to provide industry with a lot of data regarding your process as a whole. And after the chemistry development, the process is transferred to engineers, and they have a lot of data as well. So it's yeah, it depends. It depends at what stage of the project you are.
Thank you. Here we have another question. It says, what kind of qualities do you look for in students?
Motivation. I need to see this spark in the eyes, nothing else. The rest, we can train you, no problem. You will learn everything. We will help you to learn these things, but we need to see your motivation.
Okay, thanks. And there is one participant who raised a hand. If you want, you can use your microphone and ask question.
No, I'm sorry, it was accidentally.
Oh. Okay, so are there any other questions? Okay, guys, don't be shy to ask questions.
Yeah, everybody afraid of chemists for some reason. I don't know. It's we do not bite. We're actually friendly.
So, Professor, you already have a group of students who are working with you on your projects. Are you planning on adding some new people on your group?
Always. And I really recommend students to start looking for research opportunity probably after the first year of their bachelor studies, because it takes a while to to learn things, to adjust to the lab conditions and things like that. And if you're starting as a third year, so finally by the end of the fourth year, you can do something and really produce some really cool results, but you have to leave. And this is not very ideal situation. And yeah, I'm looking for freshmen. So my first students at Nazarbayev University, I just grabbed them from the general chemistry laboratory. So at the end of their first year, and because it's I like them fresh, you know. So otherwise it's too late, you know, and you spend the year kind of teaching them the techniques, the chemistry theory behind the projects and things like that, and then we have to get something back in return, right? So from them, but it's not about us, in fact, because it's nice to see when students produce cool results, because again, motivation is very important. And if student is producing cool results and producing publications, cool publications during their bachelor studies, so most of them become motivated to go to graduate school and continue their education in these fields. All right, so and it affects their careers, and any research takes time. All right, so I really recommend students to start as soon as they can, but maybe after the first year, because first year they have to focus on studies a little bit, so they have to understand the requirements of the programs. So it's a big of a challenge for the students to switch from the high school or from the CPS programs to the programs at the departments, because it's a lot more complicated. So therefore, after the first year, that's the best time. So there was another question. Do you take motivated students for research with no chemistry background? Well, you have to have some chemistry background, high school chemistry at least, right? Or you didn't have any background in high school? So if there is no chemistry background, this is difficult, because we cannot really explain in the lab the material of general chemistry and things like that. So simple things, how to calculate the reaction, how to operate with moles, how to operate with the stoichiometry. So these are essential. If the student doesn't have any knowledge in these kind of things, in general aspects of redox reactions, of Lewis acidity, Bronsted acidity, and things like that. So I would spend only 5 years teaching the students all the basics. So, and when we're gonna do the research? So that's a problem. So we have to have some background. Students can be not strong in chemistry, in particular field of chemistry, but that's fine. But the basics is necessary.
Thank you. Here we have another question. It says, how could new students be recruited given the current conditions, like the online education? Yeah, maybe.
Well, right now it's tough. It's well, I hope, and we all hope that the situation will improve soon, and we return back to face-to-face studying and doing research. And in this case, we can meet and talk and discuss things, no problem. I'm always looking for motivated students, and I always need hands. So it happens all the time. Then when you have more ideas than the hands to do the ideas, you know. So and if not, at least we can start discussing things right now, because students also have to read some research literature about the projects and things like that. And this online mode of education, it's a perfect time to do that, become familiar about things within the project. And frankly speaking, in order to get any ideas regarding certain chemistry or certain projects, you have to read scientific literature. This is the only way how to get any ideas. And it's always cool when student comes to the lab and just tells you, oh, I have an idea, let's do it. It's like, well, if it's reasonable, yeah, why not? So at least we can get in touch and start discussing things online. And hopefully, in a fall semester, everything will be back to normal. And in this case, we can just meet in person and talk about particular details and other things.
So basically, is it enough to just email you and show some interest?
Yeah, it's always enough to just email me. Guys, I had a lot of internships and you know, I had a lot of internships invitations where I didn't go even when I was a student. And I went online, found the professor either in Germany or in Sweden, and just emailed the professor introducing myself. I'm that, and that. So I would like to do some, you know, collaborative research in your lab during a few months in the summer. Can I come? Do you have funding for me? So, and usually they say no, but sometimes they say yes, in fact, and sometimes they just encourage you to apply for some internship or the fellowship together with them. You get it, you go. So it's that simple. Don't be shy. I mean, professors do not bite. Just talk to us. We're also people.
Okay, thank you very much. I guess we have no other questions, and we can finish our today's session. So, Professor, huge thanks for joining us on providing the remote lecture sessions. We have heard about wonderful projects. We wish you the best on them. And thank you for thank you, students, for joining and for asking interesting questions, for getting involved with the research. We want you more to be involved in this. And thank you for the Nazarbayev University professors for providing this opportunity for the students. So thank you for.
Well, thank you guys for organizing all this. I think it's a very good initiative, and it actually makes students be familiar with what's happening at Nazarbayev University, and I think it's really cool.
Mm-hmm. Yeah, thanks very much. So tomorrow we have another lab tour. If you are interested, please check our social media accounts, Instagram, Telegram. We publish all the fresh information there. And if you have missed some part of this lecture, don't be afraid. We are going to upload this lecture on our YouTube channel, and of course we will notify it by using the Instagram and Telegram. So once again, Professor, thank you very much. We wish you the best of luck, and thank you all for coming. This is it for today.
Thank you. Bye-bye.